We've been talking about bonds within molecules, actual chemical bonds, what we could call intramolecular forces, the forces that hold the atoms together to make a molecule. Now, as we venture into selected topics from Chapter 8, we're going to take up intermolecular forces. These are forces between molecules, right? The kinds of forces that would get molecules to coalesce together to form a liquid or a solid. We know these forces exist. We know they're one of the reasons why the ideal gas model fails under certain conditions, right? We've talked about that back in Chapter 5. The plot here is one that sort of illustrates that. This is PV over RT for 1 mole of gas as a function of pressure. Right. Some of you will find it odd that pressure is both in the expression on the y-axis and is the x-axis. But if you think about it, PV over RT would be equal to N for an ideal gas, right? So if I have 1 mole of gas, then for an ideal gas, this stays equal to 1 at all values of pressure, which is what the dashed line through the center of the graph there suggests, right? There are plots on this figure for 4 common gases, and you can tell that they all deviate from ideal behavior to various extents under different conditions, right? If I go out to the right-hand side of the graph where I'm up to 800, 1,000 atmospheres, it's maybe not surprising that all of them deviate significantly from the ideal gas model because the pressure there is quite enormous, right? You can also see more encouragingly if we come down here towards low pressure, right? And again, my scale here is in hundreds of atmospheres, right? So as I get down to the vicinity of atmospheric pressure, they all come back together and do follow the ideal gas law pretty well, which is what we would expect based on the fact we've been using that equation, the gas law, for a lot of different things, right? We can also clearly see that the extent of deviation does depend on what gas we're looking at, right? That's in large part because these forces between molecules are going to be different for those different kinds of molecules. And that's what we're going to learn about starting now. This is a table that you've seen before back in Chapter 5. Right now, I want to focus in on the column here for A, all right? Because A is the term in this equation that corrects for intermolecular forces, okay? In particular, I want to look at where the big and small values of A are, right? The small ones are up here on the top. Helium and hydrogen, for example, have very small values of A, meaning they have very weak forces between those molecules. As I get down to the bottom, I'll see that water and HF and even SF6 down here, those have rather large values for the A constant, meaning when we start to try to explain intermolecular forces, we're going to want to be able to account for the fact that those things down here have rather strong ones, and the ones up above them in this list have much weaker intermolecular forces, right? So our understanding should reflect that because these are things that we just have to have built into whatever description we use. All right, so how do these forces arise? Again, they're responsible for the existence of what collectively we would call condensed phases. That's a fancy chemistry book word or science book word for solids and liquids, okay? Like the forces that hold atoms together to make molecules, these are also going to be based on Coulomb forces, okay? Forces between oppositely charged particles. That's what the Coulomb force is, right? The intermolecular forces are in general going to be much weaker than chemical bonds, right? The forces that hold atoms together to make a molecule are strong. The forces that hold the molecules together to make them into, say, a liquid are much weaker, right? This is reflected in the fact that when you boil water, you don't, this gas rising up off of the boiling water is not clouds of hydrogen and oxygen, it's water vapor, right? You're not decomposing the molecules, you're not taking the hydrogen and oxygens apart, you're just separating the molecules from each other and making them into water in the gas phase, okay? The various types of forces we'll consider include forces due to permanent dipoles on molecules, what are called dispersion forces, which are sort of transient or temporary dipoles, and a special category, hydrogen bonding, which is really a subset of dipole forces, but those are important in a lot of systems, and so they kind of merit discussion as their own little category. This is just an example here. This is a couple of HCl molecules, right? HCl is got a pretty big electronegativity difference, and it's a gas at normal conditions. So HCl we think of as a very polar molecule, right? What does that mean? It means that the electron cloud is pulled so that there's a lot more electron density around the chlorine, because chlorine has the big electronegativity, right? So I'm going to have a bit of a positive charge here on the hydrogen end and a bit of a negative charge over here on the chlorine end, right? Typically we would draw those as little deltas or something. I don't know why I did squiggles, but if I do that, And if the same thing happens over here, then what's going to happen? They're going to try and line themselves up so that the negative side of this one will line up near the positive end of that one. That's going to cause the force between them, right? The fact that this thing is not really just a ball, it's got some shape to it, and the electron cloud is pulled more to one side than the other. That's the origin of these forces between the molecules. All right, the strong version of the forces between molecules generally are these dipole forces, like the one for HCl there, right? To predict what molecules are going to have these dipole forces and what ones are not, we need to use the shapes of the molecules, and we need to think about a little bit about vectors, okay? Which is not a topic we delve into too often here, but bear with me, okay? A lot of molecules have a dipole moment, and that has to do with the polarity of the bonds and the shape of the molecule. Both of those things matter, okay? And so a water molecule, for example, if I look at hydrogens and oxygens, right? So remember, in my water molecule, these are my, my hydrogen atoms. Here is the white balls. That's the oxygen. All right. Oxygen has a much larger electronegativity than hydrogen, and so that means the oxygen is going to pull electron density away from the hydrogens. When that happens, there's going to be a bit of positive charge. That's what this little delta plus here means. That means a partial positive charge on the hydrogen on both sides, and there's going to be a partial negative charge up here on the oxygen. Okay, those deltas are just meant generically here as little bits of charge. We could have put, I guess, 2 delta on the top, since if there's they've got to offset and the whole molecule is not charged. But in any case, these dipoles, or this polarity, is a vector quantity, right? Meaning when the electron density is being pulled towards the oxygen, with the oxygen on the top in this case, that means there's electron density moving upward from both of them. Okay, if I take those 2 vectors and sum them, the side-to-side components are going to cancel out, right? But I'm going to be left with, as this one shows, a vector that points upward, right? And so that means that my molecule has a net dipole. It's positive on the side where the hydrogens are, and it's negative on the side where the oxygen is. Okay, that means this is a polar molecule, is what we would say, right? If I come down below, this is CO2, which has the linear structure, right? The individual bonds there still are somewhat polar, because carbon and oxygen also have different electronegativities, right? So the electrons are pulled more towards the oxygens. As this happens, if I take my 2 vectors, though, now they're pointing directly opposite from one another, right? And so if I take vectors that are the same size and they're just pointed in opposite directions, they're going to sum to nothing, right? So there is no net dipole because there is no up and down component there, and the side-to-side components are going to cancel one another out. Right, so that molecule is non-polar, we would say. The bonds are still polar, right? There's still an electronegativity difference between carbon and oxygen, but because of the way the atoms are arranged in the molecule, those bond dipoles are going to cancel. Okay, so in order to anticipate or be able to size up what molecules are polar and what molecules are not, it's important we be able to deduce their shapes correctly. Okay, and so that's something that we've been working on a little bit, and you'll need to continue to work on to sort out what molecules go in what category of these intermolecular forces. If I can tell that a molecule has a dipole to it, then what's going to happen is the dipoles are going to want to line themselves up in a way that gets the opposite charges in proximity. That's the same idea as I commented on when I had the HCl drawing up there at the start, right? Here, instead of actual molecules, I've drawn just sort of generic dipoles, just something that's got a positive charge towards one side, negative charge towards the other. Okay, either of the arrangements that is shown there will have some net attraction to them, right? Because it's got the positive charges closer to the negative charges and farther away from the other positive charges, right? So that lining up of the dipoles will cause these things to want to stick together, right? These forces, again, should be much weaker than the forces that hold the atoms together to make the molecules, but they are still substantial, and they'll influence the properties of the substances that have these, right? So anytime I have a molecule that has a permanent dipole moment, I should expect these dipole forces to probably be the dominant form of intermolecular forces between them. There's another category of intermolecular forces, what are known as dispersion forces. These have a lot of different names. People call them dispersion forces, London dispersion forces, or London forces sometimes, and they're also called van der Waals forces sometimes. But all those things refer to the same idea. These are the forces that hold nonpolar molecules together. right? Hydrogen and helium are as nonpolar as we can get, right? Helium is literally just a monatomic, small monatomic gas under most conditions. Hydrogen is, again, a very small molecule, clearly no charge distribution because both ends are H's. The boiling points of those are 20 Kelvin, give or take, for hydrogen, and 4 Kelvin for helium, both at atmospheric pressure. The fact that those are so low suggests the forces between those molecules are very weak, but the fact that we could eventually turn them into liquids means there must be some forces, okay? These forces are what are known as dispersion forces, and they're due to what are called induced dipoles or transient dipoles. These arise because the electron cloud in a molecule doesn't just sit in one place, right? It's kind of drifting around, right? We say that on average, the electrons are evenly distributed, but that doesn't mean they're always evenly distributed. And I'll talk about that momentarily. It also turns out, somewhat entertainingly, that these dispersion forces are actually what's responsible for the ability of geckos to climb on walls and things like that. The little picture on the right there is a pad on the foot of the gecko, and it has those hair-like structures on it, which what those do is they give this thing an enormous amount of surface area. And when that is interacting with something like a smooth wall, the ability to generate a lot of these little very weak forces, but over all that surface area is enough to be able to allow the lizard to climb the wall and what have you. And so there's actually a lot of work, this is kind of funny, but there's a lot of work being done to mimic the way that works and develop other things that could be used as adhesives of various sorts as a result of people coming to understand how the gecko actually sticks to the wall. So how are these transient dipoles, these dispersion forces, going to work, right? If I have a hydrogen molecule, right, I've got a hydrogen over here, a hydrogen over there, and my electron cloud around that on average should just look something like that, right? It should be more symmetric than my drawing, but well, hopefully you're used to my drawings being kind of random by now, right? If I just say I've only got 2 electrons in that cloud, right? So at any given instant, there's got to be some probability that the negative charge is all on one side or all on the other, right? My electrons, after all, are not static. They're not just locked in a place. They're sort of smeared out in space, and it's a dynamic process. And so the chances that both electrons, quote, get on the same side of the molecule have to be non-zero, right? If that happens, then I'd have a negative side of the molecule and a positive side of the molecule, right? The reason why this actually matters is because if one molecule gets in this distorted charge thing, it will actually influence the other ones nearby, right? Because if I have a negative charge, say I get a little bit of negative charge over here, right? Then any molecule that comes near that end of the molecule, the negative charge is there, it's going to push the electrons away, right? That's going to set up a similar temporary dipole in the nearby molecules. These are very weak, right? That's why hydrogen boils at 20 Kelvin, right? But it will get the molecules to line up in a way that is similar to what permanent dipoles do, okay? And so symmetric molecules, things that are not polar, that don't have a dipole moment, can still interact through these so-called dispersion forces, right? Oh, here's a slightly better looking version of that picture, or that cartoon that I tried to draw. Okay, so imagine we sort of envision having an electron on each end of the molecule, so to speak. And I know I'm kind of localizing my electrons here, but it's the easiest way to make sense of this, right? If I get the situation where on one molecule, my electrons just drift and find themselves this way, right? That puts negative charge here. If another hydrogen molecule comes up near it, the electrons are going to run away from the fact that there's 2 electrons already there, right? So now I've got these weak temporary dipoles that have shown up, and they're going to start to line up and get the molecules to interact attractively to one another, right? That's the force that holds together molecules like hydrogen. How do the strength of these forces vary, right? The strength of the forces are important because it determines what's the physical state of the stuff, of the substance, right? I've been sort of alluding to the fact that, well, the intermolecular forces for hydrogen and helium must be very weak because their boiling points are so low, right? That's because the boiling point means that's the temperature at which the average molecules can overcome the intermolecular forces, right? So as the forces get stronger, the boiling point should go up, right? Because if it's got a high boiling point, that means it's easier to get it to be a liquid. It's harder to get it to go from liquid to gas. That says the forces holding the molecules to each other are stronger, right? If my dipole forces should be stronger than dispersion forces as a general rule, right? among dispersion forces, the more electrons are present in my molecule, the more polarizable is the fancy word for this, the more polarizable it is, and the stronger the forces should be, right? So in general, things that are lighter have fewer electrons, right? And so that's one reason why hydrogen and helium has a boiling point of 4.2 Kelvin, right? That's much lower than the boiling point of neon or argon. I don't know those numbers off the top of my head, but if we looked them up, they'd be going up steadily as we went down the column, just because as I go down the column, there's more electrons in the cloud, and that means it's more likely that the distribution of charge is imbalanced, right? If I get to a point at at argon, I've got 18 electrons there, right? And so out of 18 electrons, the chances that I get a couple more on one side than the other are getting much better than they are if I'm at helium and I only have just the two, right? And so as a result, the forces get stronger as the number of electrons goes up. The stronger the forces are, the higher the melting and boiling points should be, okay? Because those intermolecular forces are what dictate, does the substance want to stay being liquid? Does it want to turn into a gas, right? If it turns into a gas at a low temperature, that means the forces are weak. If it turns into a gas or boils at a higher temperature, that means its forces must be stronger because it takes more energy, right? When we raise the temperature, we're raising the average energy of the molecules. It takes more energy to separate them from one another and overcome the intermolecular forces. This is just a further illustration of this. This is fluorine and bromine, right? So those are in the same column of the periodic table. Fluorine is in the second row, bromine is in the fourth row. And so they're separated by a number of elements, right? F2 is a gas at normal temperature and pressure at 1 atmosphere and room temperature. Bromine is a liquid at normal temperature and pressure, right? This plot shows something like the energy of interaction, right? So this is the energy between things. Where the curve is below zero, where the energy is negative, that means the forces between them are attractive, right? And you can see that the height here, this is how much energy it would take to get these things and take them up and get them be able to separate from one another, right? If the energy gets up to zero, that means they've overcome the forces and are free to come apart, okay? This height here is the average kinetic energy, the average energy that a molecule would have at 298 Kelvin, right? And so for fluorine, the average kinetic energy of a molecule is more than the amount of force that is holding them together. And that means the fluorine molecules can overcome that. And so they're a gas. For bromine, if this is the amount of energy that a molecule has, that's not enough to get me from being held together down here up to there, right? So the bromines are still trapped in that well, meaning they are still in the liquid phase, okay? The only difference between those two things, structurally, they're the same, right? They both have the same electron configurations, ground state electron configurations at least, right? And charge distribution should be symmetric. The only difference is that bromine has a lot more electrons in it because it's 2 rows further down in the periodic table. That means, again, that it is more polarizable, which means that it should have the higher boiling point, and indeed it does. So again, this just emphasizes the point that I've been making for a while now. Bigger molecules, which mean more electrons, that also means heavier, right? Because heavier corresponds with having more electrons. Those tend to have higher boiling points, okay? If I compare molecules of similar size and similar shapes, then a polar molecule would tend to have higher boiling points than a non-polar molecule, right? Because the permanent dipole forces are stronger than the dispersion forces, right? That doesn't mean that something with only dispersion forces can't eventually get to have stronger forces, right? In my table of van der Waals constants, SF6 was right up there at the biggest correction factor for the intermolecular forces. SF6 really does rely only on dispersion forces. It just has a really lot of electrons, right? And so by the time we have that many electrons in there, it is extremely polarizable, and those forces get quite strong.